So next we will show that the complex numbers is a unital algebra over the field of real numbers. So proof. As the complex numbers together with addition and multiplication is a field, there exists the identity, which is the ordered pair 1, 0 in the complex numbers, such that for every complex number z, we have that 1 times z is the same as z times 1, which is z. And therefore, the complex numbers is a unital algebra over the field of reals, since it is a algebra for which there exists a multiplicative identity for vector multiplication, that is, multiplication of complex numbers. So next, we will show that the set of reals is a unital algebra over itself. So proof, as the reals together with addition and multiplication is a field, there exists the real number 1, such that for every real number x, we have that 1 times x is the same as x times 1, which is x. And therefore, the reals is a unital algebra over itself. Okay, so new definition. A unital algebra is called a division algebra if and only if every non-zero element that is, every element distinct from the additive identity the symbol 0. So every non-zero element has a multiplicative inverse So for example, we will show that the quaternions is a division algebra over the field of reals. So proof, for every non-zero quaternion, there exists the multiplicative inverse of that quaternion, which is the conjugate of the quaternion over the square of the modulus of the quaternion, such that x times its multiplicative inverse is x times the conjugate of x over the square of the modulus. which is x times its conjugate, over the square of the modulus, which is the square of the modulus of x, over the square of the modulus of x, which is the identity 1, and the multiplicative inverse of x times x is the conjugate of x over the square of the modulus of x times x, which is the conjugate of x times x over the square of the modulus of x, which is the square of the modulus of x over the square of the modulus of x, which is the identity 1. And so every non-zero quaternion has a multiplicative inverse, and therefore the quaternions is a division algebra. Over the field of reals. So notice that we have demonstrated that the non-zero quaternions, together with multiplication of quaternions, is a non-abelian group and so the set of quaternions together with addition and multiplication is a non-commutative division ring which is also called a skew field So the quaternions, together with addition and multiplication, is not a field, but it is a non-commutative division ring, which is also called a skew field. So whether we consider the quaternions as the set of all elements of the form x sub naught plus a three-dimensional vector x, where x sub naught is a real number, and the three-dimensional vector x is a three-dimensional real vector, or if we consider the quaternions as the coordinate space R4, which is the set of ordered quadruples x sub 1 through x sub 4, where the elements x sub I are real numbers, or if we consider the quaternions as the algebraic extension of the reals to include real multiples of the numbers I, j, and k, where x sub I is a real number, and the quaternion units I squared is equal to j squared is equal to k squared, which is the same as I times j times k, which is -1. No matter how we consider the set of quaternions, the quaternions together with addition and multiplication is a skew field and the quaternions is a four-dimensional associative division algebra over the field of real numbers. So next, we will show that the complex numbers is a division algebra over the field of reals. Now for every non-zero complex number, there exists the multiplicative inverse, which is the conjugate of the complex number z over the square of the modulus of that complex number, where the conjugate is the ordered pair x negative y over the square of the conjugate, which is x squared plus y squared. So for every non-zero complex number, where we consider the complex numbers as ordered pairs of real numbers, there exists a multiplicative inverse, which is the conjugate of the complex number z over the square of the modulus, which is the sum of the squares of the components, such that z times its multiplicative inverse is the ordered pair xy times the ordered pair x negative y over the sum of the square of the components x and y, which is the ordered pair whose first component is x squared plus y squared, and whose second component is x times y minus x times y over x squared plus y squared, which is the scalar x squared plus y squared times the ordered pair 1, 0 over x squared plus y squared, which is the identity, the ordered pair 1, 0. And the multiplicative inverse of the complex number z times z is the ordered pair x minus y over x squared plus y squared times the ordered pair x, y, which once again is the ordered pair x squared plus y squared as the first component, or real component, and whose second component is x times y minus x times y over x squared plus y squared, which is the scalar x squared plus y squared times the ordered pair 1, 0 over x squared plus y squared, which is the ordered pair 1, 0, which is the identity, multiplicative identity. And therefore the complex numbers, for every complex number, every non-zero complex number, there exists a multiplicative inverse such that the product of the complex number with its inverse in whichever order gives the multiplicative identity, and so the complex numbers is a division algebra over the field of reals. So notice whether we consider the complex numbers as the coordinate space r squared, in which case we consider the complex numbers as ordered pairs of real numbers, or if we consider the complex numbers as the algebraic extension of the reals to include real multiples of the number I, where I squared is the real number -1. The complex numbers, together with addition and multiplication, is a field And the complex numbers is a two-dimensional commutative and associative division algebra over the field of reals. So next, we will show that the reals is a division algebra over itself. So for every non-zero real number, there exists a multiplicative inverse, which is the reciprocal of that real number, such that x times its multiplicative inverse is the identity, the real number 1, and the multiplicative inverse of x times x is also the real number 1, which is the multiplicative identity. And so for every non-zero real number, there exists a multiplicative inverse for which the product of the real number x with its multiplicative inverse in whichever order gives the multiplicative identity. And so the real numbers is a division algebra over itself. So notice that the reals together with addition and multiplication is a field, and the set of real numbers is a one-dimensional commutative and associative division algebra over itself. Now there is a theorem known as Frobenius's theorem, which states that every associative division algebra over the reals is isomorphic to exactly one of the following. The set of reals itself, which again is a one-dimensional division algebra, which is associative and commutative. The complex numbers, which is a two-dimensional division algebra, associative division algebra over the reals, that is also commutative. And the quaternions, which is a four-dimensional associative division algebra over the reals, which is not commutative.